Understanding 3D data. From XYZ coordinates to evolving structures in the digital age. In today's data-driven world, 3D data has become a cornerstone of industries ranging from gaming and animation to engineering, medicine, and geospatial science. But what exactly is 3D data, and how has it evolved over time? The foundation: X, Y, and Z coordinates. At its core, 3D data is about describing objects or environments in three-dimensional space. This is typically done using the Cartesian coordinate system, which defines every point in space with three variables: X, horizontal axis; Y, vertical axis; Z, depth axis. These coordinates allow us to locate and manipulate any point in a virtual or physical 3D environment. For instance, a point 3 minus 2.57 tells us exactly where something is located relative to the origin 0, 0, 0. These values can be positive or negative, integers or decimals, depending on the precision and range needed. Decimal precision and scale. As 3D modeling has advanced, the ability to work with decimal values, floating point numbers, has become essential. Precision is critical in applications like medical imaging or CAD, computer-aided design, where even a 0.001 unit discrepancy can be significant. Modern 3D systems use floating point arithmetic to represent tiny fractions or massive coordinates. For example, 1.234 minus 0.005, 200.009 might represent a surgical tool's tip. 10,500.87, 9,000.33, minus 1234.44 could represent a satellite component in space. Data structures in 3D environments. 3D data isn't just a collection of isolated points, it's organized into structures. Some of the most common include meshes, composed of vertices, points, edges, lines, and faces, polygons, usually triangles or quads. Meshes define the surface of a 3D object. Point clouds. Large sets of data points in space, often generated by 3D scanners like LiDAR. Voxels. 3D equivalents of pixels, used in volumetric data, like in medical CT scans. NURBS, non-uniform rational B-splines, used in high-precision modeling for smooth curves and surfaces. Each structure serves different purposes. For example, gaming engines prioritize low-polygon meshes for performance, while architectural design tools might use high-resolution NURBS or BIM, building information modeling data. Representing 3D objects. A 3D object might include geometry, position, size, and shape. Topology. How different parts connect or relate. Materials, color, texture, and physical properties, reflectivity, transparency, etc. Transformations. Movement, translation, rotation, and scaling in the 3D space. This combination allows digital systems to simulate real-world physical behavior and appearance. The evolution of 3D data. Over the decades, 3D data has undergone a remarkable transformation. 1960s, 1980s. Basic vector graphics and wireframe models in CAD. 1990s. Introduction of textured meshes and real-time 3D graphics in video games. 2000s. Rapid growth of 3D scanning, motion capture, and photorealistic rendering. 2010s. Cloud-based modeling, real-time simulation, R/VR, and machine learning applications. 2020s today. AI-enhanced 3D reconstruction, volumetric video, metaverse platforms, digital twins, and more efficient data compression and streaming. Modern 3D systems now rely heavily on standardized file formats like .obj, .stl, .gltf, .fbx, and API such as OpenGL, WebGL, or DirectX to manage and share 3D data across platforms. Conclusion: 3D data is no longer confined to specialized industries, it's part of our everyday lives, from navigation apps and medical diagnostics to movies and online shopping. Understanding its foundation in X, Y, Z coordinates, its structural organization, and its evolution helps demystify the digital worlds we increasingly interact with. As technology continues to evolve, so too will the complexity, realism, and ubiquity of 3D data.